with week 5 session. So here are some couple of questions, and I hope you have already seen the lectures online. So I hope you will simply start answering these questions. They are very easy, and most of the definitions we have discussed in the previous tutorials. Okay. So question 1 is in the case of a real Brayton cycle, the turbine pressure ratio, is it greater than or lesser than the compressor pressure ratio or equal? So what is the answer? Hello? Yeah, what is the answer here for a real Brayton cycle? Is it greater than or lesser than compressor pressure ratio? Yeah, so the answer is lesser than. Why? The main work of turbine is not to increase the pressure ratio, it is decreasing the pressure ratio. No, but that's not how you define the pressure ratio, right? So how would you define a pressure ratio here? So let us first consider the most ideal case. Okay, so let us say on your TS diagram, so this is your compressor, then from there you have the combustor, and then you have a turbine, right? So ideally what we would want is that the work of the turbine is same as the work of the compressor. So in an ideal situation, what is it going to be? The rise in the compressor, the pressure rise in the compressor should be same as the pressure decrease in the turbine. So you will define the pressure ratio for the turbine as what? So if these are the stations 1, 2, 3, 4, so pressure ratio for compressor is going to be P2 by P1. Okay, and the pressure ratio for turbine, of course in turbine the pressure ratio is decreasing, but we will define the pressure ratio as P3 by P4 so that we can compare the pressure ratio of the compressor and turbine. So in an ideal situation, what will it be? Yeah, you just answered right now. Hello, am I audible? Okay, please answer quickly so that we can move on. Yeah, please tell me. No, this is already ideal situation. Okay, I have drawn an ideal Brayton cycle. So what I am asking is, for this case, the ideal case, what is the relation between the compressor pressure ratio and the turbine pressure ratio? No, you're right that the pressure ratio will be same, but that's not because P2 is equal to P3. So P2 is equal to P3, but also we should remember that P2 by P1 is equal to P3 by P4, because in an ideal situation the work input over here is equal to the work output over here. Okay, so whatever pressure rise is happening in the compressor will be equal to the pressure decrease in the turbine. But what happens in a real Brayton cycle? So now let us consider the real process. So say we achieve the same pressure ratio in the compressor, okay, but in the combustion chamber what is going to happen? Because of non-idealistic assumptions, we have assumed that here the pressure remains constant, but in reality what happens is that the pressure will decrease. So I'll redraw this. So the pressure is going to decrease, and that's why the pressure ratio of the turbine will be smaller than the pressure ratio of the compressor. Does this make sense? Okay, so then the next question is isentropic efficiency of compressor is defined as what? So this we have discussed in a previous tutorial also. What is the isentropic efficiency of a compressor? Yeah, can you repeat? Can someone else answer? Is it isentropic to isentropic? Right, it's ideal work input to actual work input. So how do you define the compressor pressure ratio? So again, let's go back here. So here this 1 to 2 is the compressor, right? So we said efficiency is basically, so efficiency will be defined as what? Always remember that efficiency is going to be less than 1, and it is going to be what you get out of what you give. So for a compressor, ideally you could have got work by going from this 1 to 2 process around along this dark brown line, right? But ideally you are going along the green line. So where is the pressure rise is same, where is the work done more? In the actual process, and we know efficiency is going to be smaller than 1. So that's how we learned the definition, right? It is ideal by actual work input, and it is common sense. So in reality you will have to do more work to achieve the same pressure ratio, because the compressor will have some losses. So to achieve the same pressure ratio you will have to give in more energy, right? So what is the answer here? Answer is this option C, ideal work input to actual work input. Okay, then question 3. For a given gas and polytropic efficiency of turbine, the isentropic efficiency of the turbine, what happens with the pressure ratio? Does it increase or decrease? Any answers? Why? Why will it increase? Okay, so actually you must have derived this formula. You can relate the T naught ratios. So let us say T naught final by T naught initial, that is equal to P naught final by P naught initial, whole to the power, you will get gamma minus 1 by gamma, and there will be multiplied to eta turbine polytropic efficiency. Okay, so actually now you are saying that for the same gas, that is you have fixed gamma, if I am going to increase the pressure ratio and this polytropic efficiency is going to remain constant, then your temperature pressure ratio will also increase, and as a result your isentropic efficiency will increase, because remember the definition of isentropic efficiency was it was something like T naught final minus T naught initial divided by T naught final S minus T naught initial, right? So then because this ratio is increasing, which is in the numerator, that will lead to the increase in your isentropic efficiency. Is this clear, or any doubts are there? Yeah. No, so polytropic efficiency is fixed over here, so it is not going to affect. What is changing? Only the turbine pressure ratio. So even if polytropic efficiency was 1, then also this answer will be the same, right? So you are asking what is the effect of polytropic efficiency on isentropic efficiency. That is not the question here. You read for, yeah. Okay, so how do you define polytropic efficiency? Actually, in turbine you will have several stages, right? So for each stage, like each stage you will have a rotor, and then you will have a stator. So that's going to be like this. So for that rotor plus stator, that is together one thing called stage, right? So when you define the efficiency of the stage, that is the polytropic efficiency for turbine. And then you go on to derive the relation between this polytropic efficiency and the overall efficiency of the turbine. So then you have to simply relate that, okay, so there is some pressure decrease in this one stage, then there will be pressure decrease in the next stage, then some more pressure decrease in the following stage, and so on. And then when you take the total pressure decrease across the entire turbine, that will give you the relation between the polytropic efficiency and the isentropic efficiency. Okay, so if you increase this polytropic efficiency per stage, then your isentropic efficiency will also increase for the turbine. So that is the relation between them. Okay, so we'll move on to question 4 now. For the Brayton cycle, the isentropic compressor work input is always is it higher or lower than the work input? Okay, so I think this is a simple question. And the previous case also, yeah, fine. Okay, so we'll move on to question 5. This is a numerical now. Okay, this is simple actually, because see, this is just using the adiabatic relations. So what you are given is the Mach number. Okay, so I'll start writing this. Mach number is 0.7, and the speed of sound is given. So speed of sound is 340 meter per second. What is the formula for speed of sound? Under root gamma RT, right? And then they're asking you to find the total temperature, which is T naught. So what is the formula for T naught? Right, thank you. Okay, so this is the formula. So here we just need this temperature T, which you can find by substituting the values over here, because speed of sound is given and also Mach number is given. So please calculate. First tell me what is T value, and then tell me what is the value of T naught. What is the value of the static temperature? You just have to use this equation. Yeah, okay, so this is 287.70 Kelvin. And then what is T naught? So you just substitute this T value here. You have the Mach number, R is given, gamma is given. So what is T naught? Yeah, 315.89. So from the options you can see that it is approximately equal to 316 Kelvin. Okay, I hope everyone got this answer. So I'll move on to the next question. So here again, see, we are given the pressure, that is the static pressure.
Expressions of quantity tell us how many or how much of something there is. Compare these two sentences. We get a little rain in spring.
Just a second. Yeah, okay, so we are given the pressure and the Mach number. So pressure is given to be 1 bar, Mach number is 0.88. Then the stagnation pressure at that point is going to be what? So what is the relation of P naught with the static pressure? Right, so this whole raised to gamma by gamma minus 1. Okay, so now just please calculate and tell me what is the value of P naught that you get. 1.65. Okay, so that is there in the options as well, option A. Okay, so now we'll do a big numerical, that is we'll solve a real turbojet cycle. Okay, so here what is given, a gas turbine power plant consists of a two-stage turbine uh, based expansion and reheater. Air enters the compressor at 1 bar, so the inlet conditions are given, 1 bar pressure, 24 degrees Celsius. The maximum temperature of the cycle is limited to 1050 Kelvin, so maximum temperature will be achieved in the combustion chamber, and the pressure ratio is 5. So pressure ratio is given for the compressor and also for the turbine. Okay, after the first stage of expansion, air is reheated to 1050 Kelvin such that the expansion work output becomes maximum. Okay, so the isentropic efficiency of compressor and turbine is given to you. Now this is where you will use the equations for real compressor and turbine components. Okay, and then based on this data you have to basically calculate the temperature at the exit of compressor and all these questions. So you can see the diagram here and take help of that. Okay, this is ideally supposed to be at the same level 3 and 5 because they will be at the same temperature, which is T max. Okay, so first you have a compressor, then combustion chamber, after that turbine, which is the first stage of turbine, and what you do after that is you reheat this air, and you reheat and bring it to the maximum temperature, and then finally you allow it to expand through the second stage. So this is the entire process. This is clear, right? Yeah. Turbine is optimized or not, as in? I don't understand your question. Yeah. So actually they want maximum work output. See, you can read here. They have I don't think so because there is but remember that is only for an ideal case. The T4 will be equal to T6, but that is in the ideal case. Now we have real scenario, right? So the only thing I will assume is that T3 is equal to T5 because that is given very clearly. Now whether T4 is equal to T6 or not, that we cannot assume because we have some efficiency of the turbine here, right? Okay, I would not like to assume that still, because see what happens is, say for example you have the same efficiency, right? So 3 to 4s would be the same drop, right? And then from 4s, if you are raising it to the same temperature and then coming you're allowing expansion, then the temperature that you would reach would be the same. That is what we are saying. But now because there is some real processes involved and there are some losses, actually this particular state is not going to remain the same, right? So 5 to 6s, I do not expect it to be the same. Are you understanding that? So 3 to 4s and 5 to 6s, I don't expect it to be the same. It might turn out to be in this case because the efficiencies are same, but ideally you should not assume anything like that, and especially if all the information is given, it's best to just do the calculation. Okay, otherwise the entire process is clear, right? What we are doing over here. Yeah, right. Okay, so let us start solving this particular question. So the first thing we have to do is we have to solve for the exit temperature of the compressor, that is T2. Okay, and we are given P1. So what was P1 over here? P1 is 1 bar. Okay, and T1 is 24 degree. So now come on, tell me, what do we do next? Yeah, so that we can apply the adiabatic relations between state 1 and state 2s, right? So you'll say P1 by P2 is equal to T1 by T2 to the power gamma by gamma minus 1. Sorry, this will be T2s. Okay, so calculate this, and the pressure ratio is given to you, right? So this is given to be 5, I think. Yeah. So what is T2s? Oh, sorry, it should be, sorry, 5 to the power minus 1. Right. Thank you. Probably write it more carefully. So this is 1 by 5. Okay, so what is T2s here? Okay, 470.4 approximately. Okay, and then you are also given the isentropic efficiency of the compressor, which is 95%. So now apply the definition of isentropic efficiency of compressor, and from here you can find T2, right? So this definition I have told several times. I hope this time I don't have to tell the definition. What is the value of T2? Yeah, it's approximately 479.7, or you can approximate it to 480 kelvins. Okay, so that is the efficiency of compressor. I'll still write the formula, that is T2s minus T1 divided by T2 minus T1. Okay, then next step, we'll solve for the turbine. So for the first stage of the turbine, which is the high pressure turbine, for the high pressure turbine, you can see this is between stage 3 and 4, right? So here the pressure ratio is known to us, and also we know the efficiency, and we know the maximum temperature is given to us, that is T3. So T3 was given as, I think, 1050 Kelvin, right? Yeah, T3 is 1050 Kelvin. So what do we do? How can we find the temperature T4? Yes. RP1 is equal to under root RP is what you are saying. Yeah, why is that? Can you explain? Because we have two turbines, right? Two turbines, and the total pressure ratio across these turbines is RP, and across each of them, let us say we have RP1 and RP2, and we are assuming that the pressure ratio across each turbine is same, right? So RP1 into RP2 should be equal to RP. Am I right? Yeah. Okay, so from there you will get the pressure ratio for just the first turbine, which is nothing but under root of 5, right? So this will be P3 by P4. Okay, and this is also P5 by, because you are going from 4 to 5, so P5 by P6. Okay, I hope this is clear. Any doubts still here? How did we get this pressure ratio? Okay, so now that you know the pressure ratio, you can find the temperature ratio in the isentropic case, right? So given T3 by P4, I know the relation between T3 and T4S. Okay, so what is T4S now? Okay, the answer I have is almost same. It's like 836.4 Kelvin. Okay, yeah, almost same. Then you can calculate the value for oh sorry, can you repeat your answer? Yeah, right, that's 834.8 Kelvin. So now what is the value of T4? Because you know the efficiency of turbine is given to be 0.99, I think. Yeah, 0.99. yeah, I by mistake wrote that value. Okay, 836.47 Kelvin. Okay, so now it is simple. You can also solve similarly for the low pressure turbine. So we know that P5 by P6 is the same pressure ratio that we found earlier, and the relation is T5 by T6S to the power gamma by gamma minus, right? And we know T5. How do we know T5? Because there is a reheating process going on, and we are getting the fluid back to the maximum possible temperature, which is 1050 Kelvin. So now again T6S is going to be the same as you found earlier for T4S. This is clear, right? Yeah. So I think this is what you were asking in the starting. Yeah, so because the efficiency is same, then only you can say this. Yeah, only then you can say T4 is equal to T6. Okay, so then I'll just simply write this here. T6 is equal to the value T4. And okay, getting back to the question. So we have already found the actual temperature at the exit of compressor, which was T2. Then next you have to find the summation of the heat input in the combustion chamber and reheater. So first there is some heat addition here, so I'll call that Q1, and there is some heat addition here, which I'll call Q2. So how will you find this total heat input? Q total is Cp T3 minus T2, I could not get the last part, plus Cp into T5 minus T4. Okay, so we have all these values, right? And Cp is also given. So what is the value of the total heat that you have got? I'll show you the value of Cp if you want. Cp is given to be 1.005 kilojoule per kg Kelvin. There's a lot of disturbance in your voice. If you can say it more loudly. Yes, 787.9 kilojoule per kg. Alright. Okay, so that is the total heat addition. Okay, so then next question is, what is the net work output of the plant? So what is the formula for net work output? Times any one of the turbine work, okay, and minus work of the compressor, which I can find as 2 Cp into what? plus what oh sorry, minus, yeah, minus T2 minus T1. Fine. So again you have all these values. Always remember that in these calculations, when you are calculating the work or the heat, always use the real temperatures. So never use the isentropic values, like don't use the value of T2s or T4s and so on. Okay, so you have all the values. Please tell me the answer. What is the net work of this cycle? It's 245.7 approximately what I have here. Yeah, you were pretty close. Okay, so then the next thing we have to find is work ratio. So work ratio is nothing but the net work by the turbine work, and that is equal to what is the work ratio? So you would have found the turbine work also here, right? 2 times the work of one turbine. No, yeah, right, 0.57. Okay. So what did you use in the denominator? You should have used 2 times the turbine work. 2 times the this particular part. This is what you will use in the denominator here. Is this clear to everyone? Yeah. Okay. Okay. Then you have to calculate back work ratio. So do you know what is back work ratio? Compressor work upon turbine work, the total turbine work, right? I think I should not confuse, because here I have written WT. So yeah, I should write total. Okay. So then what is the answer? So there is nothing but Cp into T2 minus T1 divided by 2 times Cp into T3 minus T4. So what is the answer? Yeah, it's approximately 0.43. And you can also find the thermal efficiency. So thermal efficiency is what is the definition here now? Net work divided by Q, the total heat input. So don't forget to add the work from the heater. So what is the answer now? You found all these values earlier. Just plug it in. Yeah, 31%. Yeah, 0.31. Okay. Okay, so that's all for today's assignment actually, unless you all have some questions and I can try to answer that. Are there any more questions or any questions from this assignment? Okay, I'll go to week 4 then. This one itself, right? Is this the question you're talking about? Oh, okay. No. Those assignments I cannot tell you, because they are the assignments which are going to get you the marks and all. So I'm not supposed to solve those questions. Okay, then you'll have to tell me the question, because I don't have access to those questions right now. Okay. You're saying, okay, we have some intercooling and reheating. Both are there. Yeah. So, what is the question? tutorial. No, that I agree, but previous week tutorial, I think nobody turned up, and there we discussed this. So what is the effect of regenerator on the thermal efficiency and reheater? So all this was discussed. Have you seen this particular assignment before? Yeah, okay, then I'll please ask you to see this, because all this was discussed clearly. But anyways, let me answer it in short here. So when you add a reheater, for example, so where do you add a reheater? It is between a high pressure turbine and a low pressure turbine, right? So what you are doing is, see, the idea is always, if you expand a very high temperature gas and a high pressure gas, then you expect to get more work from that, because if it is at high temperature, then it has more energy and you will be able to extract more kinetic energy from that gas. Okay, so what we do, the idea is that from high pressure turbine, whatever gas you got at state 4, you will expand it, you will heat it and raise its temperature at constant pressure. Okay, and then at this high temperature you will allow it to expand. So now tell, what was the question? What is going to happen to the thermal efficiency and the net work, is it? Yeah. Okay, so thermal efficiency, what do you think? What happens? Increases or decreases? Net work is increased. Yeah. Okay, so here again, I'll tell you what happens. So in okay, let's go back to the combustion chamber. So you are raising the temperature from this particular value T2 to some T3. Okay, and this is happening at a pressure ratio which is, let us say, P2. Okay, just some pressure over here. And then after the expansion, you have decreased the pressure, and now you need to raise the temperature. So whenever you raise the temperature at lower pressures, and you are raising the temperature starting from T4, here you were raising the temperature starting at T2. Okay, so you need to see the initial condition. Now in the case of a combustion chamber, you are starting at slightly higher pressures but at much lower temperatures, and in the reheater you are starting at slightly lower pressures but at very high temperatures, and in order to increase the temperature from T4 to T5, which is from high temperature to very high temperature, you will need more energy. Do you agree with me? Yeah, so if you need more energy, you need to add more fuel. So even though the net work has increased, of course the amount of heat that you need to add would have also increased dramatically. Yeah, so that's why. And increasing the temperatures at lower pressures is more difficult. That is why in an afterburner, if you compare the thermal efficiency of a combustion chamber and an afterburner, thermal efficiency of a combustion chamber is much more, because there the pressure was initially high coming from the compressor, but when the fluid has expanded in the turbine and then you send it in the afterburner, or in here in the case of a reheater, what is going to happen, that you are adding heat to raise the temperature from pretty high temperature to very high temperature, and that is at lower pressure. So you need to add a lot of fuel over there. So I would say that the thermal efficiency will decrease. Okay. Okay, so for afterburner, this is a very well known fact, because see, in afterburner you are not raising the temperature from just 4 to 5, it goes much beyond. The temperatures will be much more than this T3. So in afterburner, it is very clear that the thermal efficiency is going to decrease. So in reheater, if this increase is very small, then it is difficult to say. But say for example, the pressure ratios, like I said, if you are comparing this pressure at P2, P2 is equal to P3, and then you compare that with P4 and P5, they are approximately same, then I will agree with this, that it's very difficult to say about the thermal efficiency. But if the pressure ratios are dramatically different, so it is difficult to add more heat at lower pressures. Okay. Yeah, so that was one of the. Oh, okay. Okay, let us see what happens in an intercooler. So in an intercooler, what are we doing? So we start with this. I'll see the TS diagram. We start from state 1. Okay, we increase the pressure ratio in first stage, that is compressor first stage. And then what are we doing? We are decreasing the temperature. We are allowing some heat to be released, and then we further increase the pressure. So now you are achieving the same pressure ratio but at lower temperatures, right? Okay, so I don't know how this is going to affect the thermal efficiency, because see, the pressure ratio is going to remain same, isn't it? So the work input to, yeah. Sorry, can you repeat yourself? We have not decreased the compressor work, because see, the compressor work will be measured by this ratio, isn't it? Oh, but the temperature has decreased, so yeah, the work input to the compressor has decreased. Yes. Yeah. Yes. Yeah, you're right. So here efficiency is increasing. Hmm. Yeah. So by intercooler we can increase the efficiency. Okay. Okay. So if you use both intercooler and reheater, and intercooler is increasing the efficiency and reheater may or may not increase the efficiency, we cannot say. I mean, see, what if it or what if the decrease is much more here? Oh, okay. Yeah, yeah. Please. Because of adding intercooler, the efficiency will not increase, right? But it is affecting the temperature. It is affecting the temperature, so that is going to change things. How do you calculate the work? You will calculate the work by saying, here in this case, compressor stage 1 work will be this temperature, whatever you have reached here. So let us say that is state C, I can see over here. So it will be Tc minus T1 into Cp, plus in stage 2 it will be Cp into T2 minus Td. So if this total work is lesser than the normal situation, which is T2 prime minus T1. Okay, so you are saying that in intercooler, no, no. I mean, if I don't, even if I don't see the intercooler, actually actually there is another thing. So you have decreased the temperature, right? But if you have decreased the temperature, then to bring it to the same maximum temperature, which is like some T max, now initially you would have to add heat enough to get it from 2 prime to T max. Now what you have to do, you have to start from T2 and get it to T max, so you will have to add more heat. Okay, so even if you have brought down the network input, you have increased the amount of heat that you need to add. Am I? No, you can't say. No, I don't think so. Yeah. Yeah. No, but then how will it increase? Because see, if the network is increasing, but Qn is not going to remain the same. Qn is going to increase, because that's what I'm saying. So you have to start in the ideal situation without the intercooler. You have to start from T2 prime and go to this T max, right? But now you have to start from a lower temperature and go to the same T max. So don't you have to add extra heat? So your Qn is also going to increase and network is also going to increase. And like she said, intercooler will also come at some cost. So you can't say that the efficiency has increased. So in the case of a reheater, I am pretty sure that the efficiency will mostly decrease. Right, from the logic that adding heat is difficult at lower pressures, and already you are starting at, yeah, so this is like kind of clear. But for intercooler, you can't say anything. It will definitely not increase, because heat input will be either proportional to the net work increase, right? So how much ever net work increases, the heat input will also increase as much, or it will be much more. Right, so I would think that the efficiency would either remain same or decrease. What is the significance of this attachment? So efficiency is not increasing, okay, but no. So efficiency is not increasing, but net work is increasing, right? So in different engines or different purposes. So how do you decide which engine to use? You see what is your mission. Now if your mission requires more efficiency, where do you require more efficiency? In what type of aircrafts? Where do you need more efficiency? It is in civil aircrafts, right? Yeah, but in some other aircrafts, or maybe in gas turbine engines, which are used to produce electricity for households, domestic purposes, there maybe you need, in some countries, if they say they want more efficiency, and some other countries they say no, I want more work output. Yeah, so then it depends on your purpose. That's why you are either going to use intercooler or reheater.